Geoffrey West, Scale, the Universal Laws of Growth, Innovation, Sustainability, and the Pace of Life in Organisms, Cities, Economies, and Companies. Welcome to the magical world of scaling, the fascinating patterns and phenomena that govern our complex world. In a scale, the universal laws of growth, innovation, sustainability, and the pace of life in organisms, cities, economies, and companies. Geoffrey West takes you on an intriguing journey of the rules that underpin biological and socioeconomic life. From understanding the intriguing straight lines formed by plotting metabolic rates of animals to the unseen connections among New York, Paris, and Sao Paulo, you'll discover scaling relationships and their implications on human existence. Navigate through this summary filled with mind-blowing information on how biological and human networks function, along with the insights into the future of our world.
The incredible patterns of life. Earth is home to numerous species and diverse cultures, which can be overwhelming to comprehend. However, behind the complexities of biological and socio-economic life are surprising systematic patterns. Scaling relationships play a significant role and lead to incredible correlations that are not mere coincidences. For instance, there is a perfect relationship between the metabolic rate of animals and their body mass. Likewise, the total number of heartbeats in an animal's life is also related to body mass, producing a straight line. In economics, the number of patents registered in a city scales 15% faster than the city's population. Understanding this phenomenon can help to illuminate much about the world. Scientists study mice to model the way new drugs will affect the human body, which seems impossible since mice are much smaller than humans. But scaling can explain the answer. The article explores other incredible examples of scaling relationships that explain organisms, cities, and even companies in the subsequent parts. Scaling laws and the lack of real-life Godzilla. Learn how scaling laws explain that a creature like Godzilla cannot exist in real life and the practical implications of nonlinearity. Godzilla might be a thrilling character in movies, but in real life, he would not survive due to the nonlinearity of scaling laws. Though scaling laws do not work linearly, most people might dismiss the idea of nonlinearity and find the characteristics of such a giant monster purely hypothetical. In the 17th century, Italian physicist and mathematician, Galileo Galilei, had already demonstrated how scaling laws do not follow a linear pattern. When scaling up each side of a square foot to 3 feet, the area becomes 9 square feet instead of 3. Similarly, the volume of a 3-foot cube becomes 27 cubic feet, meaning that if the cube's sides are tripled, the volume will increase 27 times. However, length and strength only increase by the factor of 9 and 3 times, respectively. Therefore, if Godzilla existed, it would be 60 times heavier than his bones could bear, and his bones would break instantly. The nonlinearity of scaling laws not only explains the practical implications of Godzilla's defeat but also extends to other sectors, such as transportation. In the 1800s, transatlantic steamships were dismissed as commercially untenable due to the enormous space required for fuel. However, English engineer Isambard Kingdom Brunel demonstrated that according to the nonlinearity of scaling laws, the drag forces exerted on a ship only increase proportionally to the size of the hull, which scales by the square of the ship's dimensions. Thus, the larger the steamship, the lesser fuel it needs to transport each ton of cargo. Therefore, nonlinearity explains why Godzilla is a hypothetical creature. Still, it can also have practical implications, like cost saving in transportation. The generality of biological scaling laws. According to the author, the relationship between the metabolic rate and body mass of animals is predictable and follows a scaling law. For example, when body mass increases by a factor of 10, the metabolic rate increases by a factor of 10 superscript 3. The author proposes that biological scaling laws can be explained through a network-based theory. Biological systems function through networks, which transport energy, matter, or information, and these networks have 3 generic properties: they are space-filling, terminal units are invariant, and over time they become optimized to perform better. These general systemic properties explain the hidden regularities of biological diversity and translate into mathematical language. The author believes that these properties can provide a framework to explain the regularities observed in the world. The fascinating role of the number 4 in biological scaling laws. Biological networks resemble fractals, making it necessary to extend towards the fourth dimension, which explains the prevalent use of the numbers 1/4 or 3/4 in scaling laws. Scaling laws dictate that the metabolic rate of an organism rises by a factor of 2 to the power of 3/4, less than 2. Therefore, the demand for energy increases faster than energy can be produced, halting the growth in its tracks. The book discusses more interesting examples of scaling laws from social and economic spheres. The scaling relationship between cities. The size of a city affects various aspects of life within a metropolis, and there is an underlying scaling law that applies to many of these traits. The growth of gas stations, pipes, roads, and electrical wires only increases by 85% if the size of a city is doubled. Furthermore, the 15% rule indicates that a larger city corresponds to higher wages, per capita GDP, crime rates, cases of AIDS or flu infections, number of restaurants, and patent applications. This implies that if a city with 10,000 residents and 100 restaurants doubled in population, it would have 1,150 restaurants. However, these scaling laws are only applicable to cities within the same country due to differences in affluence. Cities can also be compared to biological organisms as they function similarly and possess networked systems. Examples of such systems include the utilization of energy and resources and the production of waste and information. Moreover, urban transport networks correspond to space-filling properties as they must serve the city's residences. The Urbanocene. How scaling laws reveal life in modern cities. The author of this book believes that the modern era, which began with the Industrial Revolution in the late 18th century, can be labeled the Urbanocene. In this new period of human history, cities have become so integral to our way of life that they have influenced the very pace of life itself. According to scaling laws, life generally slows down as size increases in the animal kingdom. However, in cities, the pace of life accelerates with size. This phenomenon affects various aspects of urban life, including walking speed, social interaction, and economic activity. For example, people walk faster in larger cities. The average walking speed in a small town of a few thousand inhabitants is half that of a city with over 1 million people, where the average speed is approximately 4 miles per hour. In addition, the time people spend on the phone and the number of calls they make also increase with city size. This was determined by analyzing cell phone data, which found that people in Lisbon, a city of 560,000, spend twice as much time on the phone and call twice as many people as those living in Lixa, rural Portuguese town of 4,200. Although the number of businesses within a city increases with population size, the diversity of businesses increases only very slowly with size. For instance, doubling the population of a city leads to only a 5% increase in business diversity, on average, although the total number of businesses will double. In conclusion, this book explores the impact of city size on various aspects of modern urban life and how this has given rise to the Urbanocene era. The use of scaling laws helps us understand the accelerating pace of life in cities and how it affects our social and economic behavior. The scaling patterns of businesses. Businesses follow specific scaling patterns as they grow, with sales, expenses, and profits increasing regularly relative to the number of employees. A company's age also has a significant impact on its growth rate, with most firms experiencing rapid growth in their youth before slowing down. Interestingly, a company's age can predict its chances of survival, with around half of all publicly traded businesses making it past the 10-year mark and only a tiny fraction surviving for over 200 years. This law means even the most successful companies, such as Apple, Google, and Facebook, will eventually meet their end. Regardless of sector, location, or size, clear patterns emerge based solely on the size and age of a business. Human population growth. The human population has been growing exponentially since the Industrial Revolution, reaching over 7 billion currently. However, there are natural barriers to the growth of any biological organism, and it's still unclear if this rapid population growth can be sustained. Thomas Robert Malthus predicted in 1798 that the food supply would grow more slowly than the population, eventually leading to the collapse of civilizations. The Club of Rome published a highly disputed study in 1972, demonstrating the potentially catastrophic results of sustained population growth. Sustainability, a global dilemma. With an ever-increasing population and economy, the sustainability of the biosphere is under threat. Traditional economic theories of an ever-expanding economic sphere are not feasible due to the finite nature of the Earth's resources. The adverse impacts of growth on the environment are inevitable and will lead to a major population crash. Although innovation could play a critical role in solving this problem, breakthrough discoveries would need to occur at an exponential pace to keep up with the problems caused by growth. A Manhattan-style project is needed to address these urgent questions of sustainability.
As our journey comes to an end, it is clear that scaling laws have a unique way of shedding light on the intricacies of the biological and socioeconomic realms. From fascinating examples in organisms, cities, and companies to the challenges of population growth and sustainability, we've witnessed the interconnectedness of our world through these universal laws. The world's future hangs in the balance, and it is vital for us to further explore these relationships, strive for innovation and sustainability, and understand the role scaling plays in our survival. These insights underscore the importance of our collective effort in preserving the world for future generations, while celebrating the beauty and interdependence of life on Earth.